Okay, hi folks. Good to kick off 2022's 101 with some work in progress. Every time I come back to this little project, I realize I've messed it up. This is about trying to come up with a decision procedure for equality in free monoidal categories. So let's what I'm basically talking about is stuff like this. So we're making we're building planar circuits from components which there's some arbitrary, these are the generators, we call them, but they could be any old thing, and they have they're oriented. They've got some inputs on the left and some outputs on the right, and it's good to imagine that as well as having that inputs and outputs of generators are not necessarily uniform. They have some sort of sort or type or whatever you want to call it. So they can only connect to compatible. Why the wires don't all carry the same sort of signal. So so what's going on? What makes these categorical? Well, for every bunch of signals, maybe I should, no, I'll stick with black. For every bunch of signals, you can just build a circuit that consists of wires, as long as you've got the same bunch of, as long as your outputs agree with your inputs in terms of their sorts. And if you have one circuit, F, say, and you have another circuit, and they agree in the middle, then you can plug them together with a sequential composition. So we've got identities and composition, and with the appropriate kind of absorption and associativity laws. So that's going to give us a category. And then you've got straightforward vertical stacking. That's going to give us monoidal structure. So so the categorical stuff is the sequential structure, and the monoidal stuff is the parallel structure. So you've got a notion of F tensor G, where you got some inputs here and you got some more inputs there, and then you end up concatenating the inputs and the outputs. And of course, the empty circuit that has no inputs and no outputs is the unit of this monoidal structure. So what we got, so the objects of this category are really the sequence of input sorts, well, the sequence of sorts that establish the connectivity of the circuit. So that's to say, monoid shows up, well, monoidal structure shows up again in the objects. The objects just live in the free monoid generated by the possible sorts. So in general, they're lists of sorts, or if there's only one sort, they are numbers. So, okay, what's going on? I could write down a bunch of equations to say which laws have to hold of these things, but actually the picture is way better, right? Because people figured out what the equations were in order to establish that you're basically allowed to deform the picture any way you can, as long as you don't cross wires. So in this case, I'm not assuming any kind of symmetry is available at all. So I can kind of stretch things, like I can pull this component this way. I can deform stuff, but no moving things past wires. So the wires are flexible, but they're nonetheless obstacles. Okay, so there's a really strong spatial intuition to which equations ought to hold. Is this making sense so far? Yep. So of course, it's clear that there's a massive amount of redundancy in how you can write so yeah, if we were doing symmetric monoidal, then the wires would be able to cross over each other. So you would indeed be able to, I don't know, do that. But some other time. I'm not saying it's not interesting. I'm saying that it's not the game I want to play today. So yeah, it's clear that if you have stuff like this, and you want to write it down, you could chop it up that way, or you could, so as a sequential composition of two parallel compositions, or you could chop it up this way as a parallel composition of two sequential compositions. But there's loads of redundancy in how you can use the sort of basic operators of monoidal categories to represent any given string diagram. So if you're trying to solve this problem by fooling about with the syntax, you got your work cut out. And so, which is not to say that it hasn't been done. There's a paper by Jamie Vickery and co, where this is figured out and turned into a lump of steaming JavaScript that actually does this. But I'm kind of, and it's very kind of what's the rewriting strategy that gets us where we want to go, and that's fabulous. But I'm thinking about this like a dependently typed programmer who loves to do big step stuff, and I want to think, well, what's the normalization by evaluation strategy for solving this problem? So correspondingly, can I get a kind of tighter grip on the notion of value in this picture? Like, what's the representation of circuits that's gonna enable me to just normalize stuff built with semicolon and tensor and get a unique representative of the equivalence class? So that's the problem, and it's a really fun problem in managing invariants precisely, and that's how I get my kicks, right? Okay, so what now? Before I go here, I want to engage in a total digression, which I will hopefully make use of later. So I'm going to just erase that stuff. Actually, maybe I will give myself more bored. Oof. Sorry. The camera will stop wobbling in a minute. Right. Okay. So I just want to think, I mean, given that the objects in our free monoidal categories are live in a free monoid, I wanted to do a digression about free monoids, or lists as we call them when we're being functional programmers. And in particular, we've got our we've got the empty list, and we've got which is absorbed by append, and append is associative, and all of that stuff. So we work with equations that say this thing is made by concatenating those things, and I want to consider the notion of morphism that you get by turning this stuff into an arrow from x's to z's. So another way of looking at it is, of course, here's x's, here's z's, and an arrow is given by some y's that makes the triangle commute. So I'm working in a slice category if you want to use the jargon, but the point is I'm working with the prefix relation. Sometimes I'll leave. Well, so the point then is I don't want to work with diagrams like the one I just drew, and that's why I rubbed it out. I'm interested in rather writing that same thing as x is a prefix of z's by the suffix y's. So the vertices are labeled with prefixes, and the morphisms are suffixes that turn shorter prefixes into longer ones. Okay, and then interesting questions include what happens if we've got some other prefix of z's, let's say w's. Right, actually, instead of giving this thing a name, I'm going to rub out that name. No, I'll put that. Okay, so here I'm saying x's is a prefix of z's, w's is a prefix of z's. Actually, what's going on here? Secretly, what information is there in this prefix relationship? Right? There's an awful lot of chat about lists and the elements in the lists, but x's is duplicated at the start of z's, y's is duplicated at the end of z's. The only actual information here is where we cut z's up. So secretly, what's going on here is just numerical calculation, right? The content of one of these morphisms is a number, just telling you where a bounded number of that, a number in the range of 0 to length of z's, telling you where you made the cut into x's and y's. Okay, so one of the marvelous things about numbers is that two numbers always have a minimum, and moreover, the minimum is one of the numbers, at least one of the numbers. It might be both of them. So that's a particular extra brilliant piece of degeneracy. So that's to say, there is some V's, which is a prefix of W's and a prefix of X's. And it is the case that if you pick any other prefix of both of them, there's a, then U's must be a prefix of V's. So instead of drawing this extra diagram, I'm just going to write this pullback corner, right? So in this case, in this category, pullbacks are finding the longest common prefix, which has to be, every other common prefix is a prefix of the longest common prefix. So in other words, secretly these things are numbers and pullback is minimum. And the marvelous thing is that the marvelous thing is that all pullback squares degenerate. All these squares degenerate to a triangle, either because this side is really an equality, or this side, or both. If I may digress from my digression, isn't it marvelous that you don't get that same degeneracy in, for example, the category you get by considering the multiplication monoid and turning that into an arrow. So what's this? This is I divides K. A morphism is a witness to the fact that I divides K. You provide the other factor J. So pullbacks in this category are greatest common divisors. And they don't have this degenerate property that the greatest common divisor of two numbers is one of the numbers. But it's fun. How do you compute greatest common divisors? You do it by repeatedly taking pullbacks, by repeated subtraction, otherwise known as computing pullbacks with respect to this monoidal structure. So it's lovely that on the one hand, multiplication is iterated addition, but on the other hand, you compute pullbacks in the multiplicative structure by iterating pullbacks in the additive structure. So isn't it marvelous that Euclid spotted that? Goodness knows, 300 BC, whatever. So once you realize that all your favorite algorithms are computing pullbacks, then life is sweet. So anyway, so this structure, that pullbacks exist, and what's more, they degenerate into triangles in this world, is may or may not be important in what follows. Okay, dolly back to dolly back to my picture. And yeah, I'm actually staring wistfully down Renfield Street, imagining going for a pint in the old hairdressers, and remembering how Jules, Fred, and I were hanging around with this this puzzle of an evening, and thinking, okay, right, how are we going to impose some sort of normal form? How are we going to resolve the kind of massive fluidity in the equational theory of the these things. Oh, hang on a minute. One other casual remark before I get there. Just a puzzle to ponder. Consider what is the free monoidal category on this generator? It's that's if you work with syntax with binding, you use the free monoidal category on this generator all the time. But anyway, I'll just leave that as a random side thought, and otherwise get on with it. Right. So okay. We got some decisions to make about how to order, and actually order is seriously important. How to manage this picture, and there are of course lots of details I'm leaving out deliberately at this stage. This is a very joined up picture, and things don't necessarily have to be as nicely joined up as this stuff, right? We notice that in this picture, all generators present have at least one input and at least one output, and everything's properly anchored to the inputs and outputs of the whole circuit. There's absolutely no reason why that should be the case. So that's a thing to worry about in a bit. Okay, so one choice to make is whether we're going to be to organize these things in a push-driven way or a pull-driven way, and arbitrarily, I'm going to go with demand. I'm going to work from the output end and figure out how I'm computing the signals on each of the output wires. I'm also going to make a decision to work from top to bottom. Yeah. So what on earth happens? Well, the game is that if you've run out of wires, you're kind of done. Actually, that's a lie. You're not done. But you can think it's if you've run out of output wires, you should think about what could possibly be remaining. And I'll try to get there. But otherwise, right? There is a first wire on the output, so you yank it and you try and figure out, like, you listen for what yelps when you yank the wire, and maybe like this wire, you find that you're actually yanking one of the inputs. Again, here I've made it the first input. Might not be the first input. You know, there could be, I don't know, there could be some stuff here, like, you know, one of those. So you need to worry about what might be there. But crucially, if the wire makes it all the way, if the wire into this output comes all the way from one of the inputs, we have chopped our space into two. So we're chopping up the inputs at a particular position. That's why I give a damn about this kind of business. And whatever else is above this position is trapped, right? It doesn't connect with the rest of the circuit. So I'm going to worry about this stuff later. Okay, so we kind of found that wire. Okay, cool. So let me get another pen. I've got a purple pen, and I'm just going to kind of chop this off. So now we move along and we yank the next wire. And this time we don't make it all the way to one of the inputs. We instead make it to an actual generator. And again, I've joined this one on at the first output of the generator, but once again, same story. There could be some mushroom there. Okay, but now what? Well, what I can do, the decomposition I can do, once I've found this generator attached to this wire, is that I can kind of do a move where I try and push this generator this way and try and pull everything else this way. So if I do that, I get this funny structure that looks like a stairway, right? In order to compute the inputs of this block, I needed some of the outputs of this one. So the crucial thing is that there are actually 3 components to the external interface of this piece, of this chunk of the circuit. There is the let me get this right. There's in order to get what was on this wire, I needed these things. I call this the shadow of the stairway, because this is the stuff that is necessarily under the stairs, right? The point is that we've minimized it, right? We're computing the shortest initial segment of the inputs that will that are required to deliver this signal. And then we also notice that what we end up with is here and here, there's a bunch of extra stuff that we couldn't help but compute on the way to computing this signal. So that's where I got to. We realized that the compositional structure that gives you kind of sensibly normalized circuit is this it's these blocks like this, where you have a shadow and a surplus. Maybe I should should call this the stair, and this is the landing. So the idea is that the landing represents the demand, right? You want to compute this stuff and you minimize the shadow and the stair. And then what happens is that the diagram splits according to what was needed for this signal and what's left over. So what we end up with is another diagram from whatever is not in shadow to the remaining outputs, and then we can play the same game again. But then, what's the how do you make these stairway diagrams? Well, it turns out that it's pretty much the same sort of logic, right? Now I'm trying to figure out how to compute the inputs to this block. So here's my landing of these three. And I can maybe have my first input is a wire here, but my second input is this generator. So now I've got myself too many colors. Another stairway inside the stairway. Okay, so so how does that work out? Let me, again, I'm going to just dolly along to some more clear board. So suppose I'm in some structure. I'm trying to build this thing, and I've got that. Then under here, I've got one sub stairway, the stairway that just computes this stuff. And then I can figure out, well, okay, how do I satisfy the rest of my demands? That's going to give me a stairway like this. And when I've split the diagram up for what the purple brick depends on and what it doesn't depend on, then there's just going to be wires in here. But how can I compute the shadow of the whole thing from the external connectivity of these two pieces? So here's the thing. I know I've got some wires going rightwards from the blue faces, and I know I've got some wires going leftwards from the red face that I've marked. But note that there's no reason for this stairway to have a shadow that is this short, right? This could carry on as far as here and actually have some more, that this shadow could be very long and actually connect all the way to the outside. So what do I have to do? I have to figure out, so we know that the blue stuff and the red stuff, that either the blue stuff has the overlap or the red stuff has the overlap, right? They have the blue signals and the red signals have a longest common prefix, which is either all of the blue stuff or all of the red stuff, or if we're amazingly lucky, all of both. If the blue stuff is shorter, then the extra red stuff becomes part of the shadow. If the blue stuff is longer than the red stuff, then the extra blue stuff becomes part of the overall stair. So once again, the key thing to achieve the composition is exactly to compute pullbacks in the category of being a prefix, with this degenerate property that the longest common prefix is one of the two prefixes. And crucially, you need to know which side the overlap is on and what the overlap is, because it's going to get tacked onto something else to build that connectivity. So yes, it turns out that thinking about this structure is the key to compositionality of these things. So that's the kind of main message, is that the compositional structure you need comes from not just thinking about inputs and outputs, but thinking about these things with three faces. These things with three faces, where there's the stuff you want to get out, the stuff you need to get this stuff out, and then the extra stuff you can't help but have. So it's tempting to say that that one of our regular circuit diagrams is made by constructing by something with a landing, by one of these stairways where the stair is empty. But of course, that's not true, because there might be, if this wasn't a stairway, remember, we're minimizing the shadow. That's the invariant, is that this is the shortest shadow that can be obscured, that can feed inputs to deliver the outputs on the landing. So there can be a whole, in a circuit with these outputs and some inputs, there could also be a load of stuff like that. To say nothing of, the fact that there could be just, you know, any old random crap that is not connected to the circuit at all, but is trapped between the wires. So that's amusing, and especially there could be, goodness knows what, there could be more of this stuff. So yes, disconnected diagrams are quite possibly the work of Satan, and actually it's only going to get worse. Right. So remember that I said that, you know, when you have just a wire that makes it all the way from the inputs from the that gets all the way to the outputs from an input, that's that wire splits the space in two. So the marvelous thing is that, let's see, give me another color. The marvelous thing is that all of the stuff that is given by just saying, oh, there's a wire from the input to a wire between input and output. So that's this wire. But it's not this wire, because this one has a generator. But then you decompose, according to this dotted purple line, and then you keep playing. So, so this wire doesn't come all the way from the inputs, but there's going to be another split here. So this wire, this wire, this wire, this one, this one, this one. Let me see if I can get this right. This one, those ones. I'm trying to figure it out. So, oh yeah, all of these ones here. Must be nearly there. This one. This wire. This wire. What I'm trying to arrange, nope, that one's wrong, is that for every enclosed region in the diagram, there is one wire which closes it, that goes directly between input and output, as opposed to causing a stairway decomposition. So we could effectively label these pink wires with some kind of payload. That's the stuff that it was trapped by this wire. And it could be anything. So we get a container-like data structure where we say the connected part of the picture fragments the plane into regions, and we're parametricing the stuff that's swilling about in the regions. At which point we then say, okay, in order to tell the story properly, what do we need to put in these pink boxes? And the answer is we need to put a bag of indeed, yes, this is very definitely 2D territory. So we're going to end up with a bag of disconnected components, and you know, when you're a functional programmer who tries to do actual stuff with actual computers and bags turn up, you think, oh shit. So it's so that's so it's, yeah, great. You know, we're going to have to figure out how to do a decent job of bags of things if we're going to deal with disconnected diagrams, and that's always a laugh. But it's important to remember the crucial well, so the key to normalizing bags is sorting. And one important piece of dirty trickery that you should always keep in your back pocket is that even if there is no sensible way to impose an ordering on stuff, there is always a way to impose an ordering on implementations of stuff. So that's the trick to getting normal focus. So we basically say, okay, you're just going to have to, when you tell me what your what the generators are, you're going to have to enable me to order the generators, and then you can impose an ordering on whole diagrams by just prioritizing the constructors from which they're built. So so there's going to be some brute force sorting involved in managing the stuff that's trapped but not connected. And so those are kind of the ingredients. It is really interesting to talk about the situation where symmetry is permitted, but there the point here is that that it's no longer appropriate to work with this structure. In fact, it's more generally the simplicial structure that you need to work with there, where you're just you're able to select anywhere, and what's important is selected or not selected rather than prefix or suffix, which reminds me the the free monoidal category generated by this thing. What is it? Anybody get there?
Thinnings.
Of course it's thinnings. It's me asking the question. So work in progress. There's all sorts of fun stuff. I mean, it's a lovely problem. Thinnings are the local local slang for initial segments of the natural numbers with monotone injections as the morphisms. So yeah, it turns out there's loads of riches in thinking about this problem, it's been a sort of monumentally joyous bit of self-inflicted nerd sniping. Yes, Delta Plus. Too many different names for these things. So anyway, I'll stop there. And it's not even 3 o'clock. How did that